Okay, so we will actually perform opening, so erosion, and then we have to decide on the structuring element. So the structuring element should follow the shapes of the main object. So this is how the main object looks like. It's a square with all one. So we will design our main object, structuring element like this. Okay, so if you perform that, then you'll find that all these will be eroded because they are not fully surrounded by one, like our structuring element, except this, the middle pixels of the main object, because it is fully surrounded by one. So then with this image, we'll perform dilation. So very simple, when you dilate, you perform all operation with this. So basically all the surrounding pixels will turn to one. Are you following? So eventually
Yes,
you
sir.
find that you remove all the small objects and you retain the main object. Okay, next, again, name 3 main classes of segmentation techniques used to find the regions that represent. So what is that? 3 main class of segmentation technique? Region, growing and shrinking. What else? Clustering method. And last but not least, the boundary detection.
Boundary.
Okay. Next. Okay. Perform suitable morphological operation figure 4 using given structuring element. This is the structuring element. So what is the suitable one? Closing or opening? Yes, closing, because you observe hole in the object. So perform closing. So what happens when we do closing? We should do dilation,
Dilation and
followed
erosion.
by erosion. Yeah. So when you dilate, so you observe that all the side pixels here will be filled with one. And this one also will be filled with one. So this is what you get after dilation. So all the red color means it used to be 0, now turned to 1 after dilation, including the holes. Okay, so next you will perform erosion based on this result. So you'll find that when you erode, all the boundary pixels will be turned to 0. But the holes that you have filled remain the same. Any question?
No, sir.
Okay. So if you don't have any questions, okay, since we have, do you have any class after this or what?
No, sir.
Anyone having class after this? I mean,
12.
no. Okay. Okay, we have no questions, then maybe we can go a little bit further to another topics. All right.
Okay.
We go for transformation. So transformation is very important. It's something to do with frequency. Okay, I'm going to skip all these lengthy mathematics. Go straight. So when we talk about transform, what we want is we want to transform, because image, all right, it is, we call it the information in spatial domain. It tells you, you know, whether the left or right, top, bottom is related to location, telling you which part is right, which part is dark. But there are other ways to represent the information. All right. So one of the ways to, for example, if I want to analyze texture, for example, I want to tell whether, you know, the surface is smooth or is coarse. Coarse means kasar, or rough. So by knowing whether it is, you know, the top or bottom is bright or dark. It's very much difficult for us to decide whether it's smooth. So to analyze texture, actually we need to transform, okay, to a frequency domain like this. So in frequency domain, what we do is we try to analyze image in terms of their frequency. In this case, if you look at the first image here, this one, you don't observe any change, it's flat, correct? So this means there is no frequency, zero, no change in the brightness across the space. And then second image, you will find that this one, you will have a gradual change from bright to dark in a horizontal way. And this one is from bright to dark in a vertically. Okay, and as you go, you can see that the change, the rate of change increased. Or in other words, the frequency actually increased. And this image has the highest frequency. You see, and highest frequency means you have a lot of changes and very frequent changes. So high frequency. So this is the pattern which we could relate with smooth. This is the smooth, and coarse. Coarse means a lot of changes. Are you following?
Yes, sir.
Yes, sir.
Okay. So where do we use this? All right. You use this when it comes to analyze texture. Like for example, we want to, like example in this case, we want to differentiate the two types of surface, the leaf of type A and type B. So type A, you can see the surface is smooth. Type B surface is coarse or rough. So if you want to differentiate the two, then you need to do transformation. And we can also use transformation to do some kind of filtering, because we know that the high frequency actually relates to very rough. So if you want to smoothen the image, you can transform and then can reduce the high frequency so that eventually the image has less high frequency or rough surface like this. So this is one of the ways for you to smoothen or sharpen image. Okay, so we'll look at the actual numerical examples. You can look at the sample of questions. Looking at the index, transformation 14. Okay. So in transformation, you'll be given image like this, and at the same time, you'll be given the basis image for you to perform the transform. So look at this basis images here. Do you see that all these basis images are associated with different frequency? This one, first one, 0 frequency, no change at all, both vertical and horizontal. And this image, we have one change from positive to negative horizontally. And this one, we have one change from positive, negative vertically. And this one will have the highest frequency where you have change in both vertical and horizontal. Okay, so how do we perform transform? So basically you have forward and in reverse. So to perform forward transform, what you need to do is to take this image and then you do a dot product with each of this basis image. Still remember dot product? Multiply 120 multiply with 1 plus with 120 multiply with 1 and so on. Are you following? Like your convolution? Hello, everybody, are you with me?
Yes. Again, sir?
120 multiply with 1. Another one, this multiply with 1. 140
Is it the same
multiply
as
with...
convolution?
Yeah, like convolution, exactly.
Oh.
Okay, so so what do you get? So basically all multiply with 1 and then add together. So what you basically sum all this together lah. So sum all this together, what do you get? 400, 500, 520 divide by 2, 260. Yeah. So you get 260 here. Are you following?
Yes, sir.
Yes, sir.
Okay, next, we want to look for why 0 here, simply because you take this and you dot with P01. So basically 120 multiply with 1, 120 multiply with -1. So one positive, one negative, so offsetting each other, correct?
Yes.
And same goes with 140 multiply with 1, 140 multiply with -1. So offsetting each other, you get 0. Okay, why we get -20 here? Because we take image and we dot with B1, 0. So you take 120 multiply with 1 and 140 multiply with -1. So practically you're taking 120 minus 140. So you get -20. And same goes with this column. Multiply with 1, multiply -1. So you are taking 120 minus 140. So you get -20. So -20, -20, -40 divide by 2. Don't forget this. So you get -20. Are you following?
Yes, sir.
So this one again, you take this and then you minus, and then you get -20. And this one is -120, positive 140. So 140 minus 120. So you get -20 here, and then you get 20 here. So eventually you get 0. Simple enough. So this is how you perform forward transform. So after transform, this is how your result looks like. Okay, so when you have this result, okay, so all this represents the intensity of different pattern. This is smooth zero frequency pattern. This is okay, maybe one change vertically. Okay, so if you look at this image, you can see that this is actually no change. Basically shows the average brightness. So the average is about 130, right in the middle, 120, 140. So difference 130. Except now because you have 2 columns, so become 260. So this zero frequency basically gives you the information about the average brightness. And then you see that why we have a non-zero coefficient here associated with B10, because you see this pattern, this is a horizontal edge, correct? And the change is from top to bottom. So that's why you find some non-zero coefficient associated with this pattern, vertical change. And you get 0 for horizontal change and diagonal change because the image has no horizontal change, okay, and no but diagonal change. Yeah, vertical change is a horizontal edge. Nampak tak? Ini horizontal edge kan? When you perform dot product, as I explained before, is you are practically comparing, you are trying to compare similarity between the image and also the image that you actually do the dot product with. So if they are not the same, then basically you get 0. If they have similar pattern like this is you know, horizontal edge, this one horizontal edge, then you get some values here, showing that they have some degree of similarity. Okay, so in short, how to perform forward transform, very simple. You just take the image, you dot product with each of this, and then you get the coefficient. Are you following?
Yes, sir.
Yeah.
Okay, next we can do some form of filtering here. So filtering, very simple. You just need to do a point-to-point multiplication with the filter mask, like this. So 260 multiply with 1, you get 260. So basically when you multiply with 1, you don't do any filter. It remains the same. Next, you multiply this with 1.5. So you get 0. And -20, when you multiply 1.5, what do you get? -30. So do you see that you actually increase the magnitude?
Yes.
So and here we multiply with 2. So when you multiply with anything bigger than 1, you're practically amplifying the magnitude, increasing it. So what happens when you increase this kind of high frequency pattern? So the image becomes smoother or more coarse, more sharp? High frequency pattern. These are high frequency pattern. This one, 0 frequency means smooth. So if you increase this type of pattern, the image becomes smoother or sharper?
Sharper.
Yes, theoretically it should be sharper. Okay, let's see what happens. So now once you have do filtering, you see you actually amplify the magnitude of high frequency. Okay, now we perform inverse. So inverse is basically you try to combine you try to compose the image again. Okay, so you take 260 multiply with B00, and then you take 0, which is this one, 0, B01, multiply with B01, okay, and then negative 30, why negative 30, this one, negative 30, multiply with B10, and then 0 multiply with B11. Okay, so you add them together. So this one multiply with half, so you get 130. And this one multiply half, you get 15. Okay, so eventually this is what you get. So now if you compare the original image, so what is the difference now? From the bright to the dark or dark to bright, the difference? How much? 30, right?
Yes.
Yes.
Okay, difference 30. Original image, what is the difference?
20.
20. So you increase the difference. When you increase the difference, the image will become sharper or smoother? Yeah, sharper. Yes, exactly. So practically, that is your intention. You increase the high frequency, so you actually push up the magnitude of high frequency. So eventually, your image become sharper. Are you following?
Yes, sir.
Yes, sir.
Okay, we look at second example. It's pretty much the same. So again, you take the image, you perform forward transform. So you do dot product with each of this, right? So you get 260, betul? Ini semua
Yes, sir.
positif. Campur-campur, bagi separuh, multiply with half. So you get 260, correct? And this
Yes.
one, if you do dot product, what do you get? Multiply 1, multiply negative 1. So practically is 100 minus 160. So negative 60. And we have 2 of them. So negative 330, 320. And again, we multiply with half. So again, we get negative 60 lah. Sorry. Ini
20, sir. 120. Negative
Yeah,
120.
negative 120, exactly. So for the first row here, we get negative 60. Second row, negative 60. So together, negative 120. Multiply with half, so negative 60. And then for this one, multiply, so 100 minus 100, 160 minus 160 is 0.
0.
And this one, 100 minus 160, so negative 60. And then 60, yeah, negative 60 plus 60 is 0 lah. Perform filtering. So again, you're increasing the magnitude of high frequency. So you should expect your result eventually will become sharper.
Yep.
So you take the coefficient, this one, the one that you have modified. So you try to multiply, okay, 260 multiply this, 120 multiply B01, 0 and 0 multiply B1011. So this is what you get. And you try to solve it, and this is what you get. So you see that now the difference increase from 70 to 190, the difference 120 exactly. So the original difference only 60.
60.
So you have actually double it. Why double it? Because you multiply with this mask. You multiply with here the 2. So you double the difference of this coefficient. That's why eventually you also double here. So compare with the results, briefly describe the effect. The effect is the difference in the pixel has been increased. So the image has become, sharpened. Has been sharpened, sorry. Kenapa macam ni? Dia, kat sini tadi sudah hilang. Okay, any questions with regards to transformation?
Sir, if the difference becomes smaller than the
Yes.
original, then it becomes smoother.
Yes, exactly. So maybe you can try with, instead of 2.0 here, you put 0.5. Okay, you can try all the values here less than 1. So then you'll find this value become less, and then eventually after you do the reverse transform, the difference also will be reduced accordingly. And then that actually shows that you have to smoothen the image.
Okay, sir.
Okay. So any questions with regards to this transformation?
No, sir.
Okay, so I'll stop recording